Alright, so now we have the notes for section 3.2, which dives more into differentiability. So 3.1 we talked about derivatives. 3.2 we're going to talk about what happens when a derivative fails to exist and the connection between derivative, linearity, and continuity. So we're going to start off with when does the derivative fail to exist at a point? So there are a few times when the derivative will not exist. The first is at a corner. So if our graph makes a corner, then our derivative does not exist. So from 3.1 we know that if the left-hand derivative and the right-hand derivative do not equal each other, then the derivative does not exist at that point. So for this first one, when we find the derivative from the left and from the right, we find that the left-hand derivative is 2 when x is less than or equal to 2, and the right-hand derivative is 0.5 when x is greater than 2. So the derivative from the left and the derivative from the right do not equal each other, therefore the derivative of f at 2 does not exist. So you might think that I worked through this problem pretty fast. I just found the derivative of the two sides of my piecewise function. So I went through and did the instantaneous rate of change to find the derivative and so on and so forth. So now for the second one, we have an absolute value equation. And if you remember from algebra, you can split an absolute value equation into a piecewise function. Okay, so we are looking at negative x cubed plus 1. That's one side of our absolute value equation. We negate everything on the inside. And then the other side of our absolute value equation would just be exactly what the inside is. So x cubed minus 1. Okay, and then our intervals for x, we're looking at what would make the absolute value equation equal to 0. So for here, it would be x being less than 1. For here, we have x being greater than or equal to 1. Okay, so 1 is what would make our absolute value equation equal to 0, so that is the point that we are paying attention to when dividing our piecewise function. So using that information, I again really quickly found the derivative of the left and the right hand side. So the left hand side derivative was negative 3x squared when x is less than 1. And the right hand side derivative is positive 3x squared when x is greater than or equal to 1. So negative 3x squared and positive 3x squared are not the same. Therefore, the derivative of f at 1 does not exist. So we can use that same logic down at the bottom and show that those derivatives also do not exist. Okay, so when we have a cusp, right, so when we have two graphs, two lines, creating a point, right, a cusp, we do not have a derivative. So there's a cusp at x equals negative 2, so the derivative at negative 2 does not exist. And then here we have a cusp at x equals 0, so the derivative at f of x equals 0 does not exist. Okay, so now on to the next page. So we also do not have a derivative when we have a vertical tangent line. So if our line ends up being straight up and down, right, if we have a vertical line, we know that the slope of a vertical line is 0 over 0, or some number over 0. So because of that, we'll have an undefined line, because we can't divide by 0. So anytime we have a vertical line, or a vertical tangent, right, because our tangent is the slope at that point, if our slope is undefined, then we do not have a derivative. So here, the derivative at 0 does not exist, because we have a vertical line at 0. And here, the derivative at 2 does not exist, because we again have a vertical line at 2. The last time when derivatives fail to exist is when we have a discontinuity. So if our function is discontinuous, right? So here we have a jump discontinuity. This function is discontinuous, therefore it does not have a derivative at x equals 3. Here we have an asymptote. We also consider these infinite discontinuities. So because we have an asymptote, there's no value at x equals 2. Therefore, the derivative at x equals 2 does not exist. Okay, so on to the next page. So being able to find a derivative and having a differentiable function means that we zoom into a function at a particular point, we should be able to see a straight line, right? We should be able to take the slope of that line, which means we should be able to see a straight line. So differentiability leads to local linearity, right? As we zoom closer and closer and closer into that point, we should be able to see a line extending. So in the example, here's our point zoomed out. As we zoom closer, right, there's still this little hump, but the closer we get to the line, we notice that it just becomes a straight line, and we can find the slope of this straight line. So as we zoom in, we can identify that there will be a derivative at this function x cosine 3x. Okay, the closer we zoom in, the more we are likely to see that line. Therefore, because our graph is continuous and differentiable, right? The straight line means that it's differentiable. The fact that there's no discontinuity means that it's continuous. We can say that f of x is differentiable at the zoomed in point. So if we look at this next graph, if we want to see if f of x is differentiable at this point here, which is x equaling 2, the closer and closer we zoom into that point, doesn't matter how close we zoom in, we will always see two lines, one going up to the left, one going up to the right. This is not a straight line. This makes a V, and the closer we get to that point, we will still see a V. Therefore, it is not differentiable. It is continuous, however, because our pen does not have to pick up off our paper to draw this line. It is continuous. However, because we do not have local linearity, it is not differentiable. So on that last page, we ran into a function that was continuous but not differentiable. So if we look at this next page, we know that if a function is continuous at a point, it might have a derivative. Okay? If it's not continuous, it absolutely does not have a derivative. But if it is continuous, it might have a derivative. So if we look at our first graph, this graph is continuous at x equals 2. We do not have to lift our pen. It is continuous. The limit from the left is equal to the limit from the right. There's no discontinuity in there, so it is continuous at x equals 2. The closer and closer we zoom into this point, our line will look like a flat line, which is still a line. Right? So the closer we zoom into our point, our line will look like a flat line. Therefore, it is also differentiable. Right? Local linearity exists here. Okay? So for this next one, we're looking at x equals 2, which is here. So again, our graph is continuous, right? There's no discontinuity. The limit from the left is equal to the limit from the right. The problem here is we have a line, but it's a vertical line. So remember, the vertical line is a vertical tangent, which means that our slope is undefined. So because we have a vertical line at x equals 2, we are not differentiable. Okay, that vertical tangent gives us an undefined slope, which means we will not be differentiable at x equals 2. So, what we can conclude is if a function has a derivative, it must be continuous. However, the opposite does not prove true necessarily. So if f has a derivative at x equals a, so if the derivative exists, then f is continuous. Okay? So if it's not continuous, if f is not continuous at x equals a, then f prime of x does not exist. At x equals a. Right? It has to be continuous for there to be a derivative. There cannot be a derivative if it is not continuous. Okay? But if f of x is continuous, there might be differentiability at x equals a. Okay? So just because it's continuous does not guarantee that it's differentiable. Okay? Just because it's continuous does not guarantee that it is differentiable. Okay, the last couple pages of your notes are talking about your calculator. So your calculator has the function of finding the derivative of a function at a point. And it'll do it for you. You just have to enter in the information the proper way. So the directions at the bottom are for a TI Inspire calculator, which I realize is not the calculator that we have at the school. So tomorrow in class, I will actually give you another version of this, just these last 2 pages that focus more on the type of calculator that we actually have at PHA. So these instructions, you can read through them. They are still similar to the instructions you'll get tomorrow, but these are not going to be 100% helpful because these are not the type of calculator that we have. So just moving on to that last section. So by looking at this, you can, however, see from this example what the derivatives are, right? So you know that the derivative at x equals 1 is -1. And you can see here that the derivative at x equals 3 is 1. Right? So this slope is 1. This slope is -1. And then here in this corner, right, the derivative on the right and the derivative on the left do not equal each other, so we should get does not exist for x equals 2, which is what we get, right? We get undefined at x equals 2. Okay, so this is just another way of seeing that the derivative does not exist at a corner. Tomorrow, when you get the instructions for the school calculators, you can work on example 3 to practice inputting the information and looking at the graph and figuring out if it does or does not have a derivative. And that is all for the notes for today.